हेलो एवरीवन, वेलकम बैक टू सी एस वर्ड। तो चलिए फिर से स्टार्ट करते हैं अपनी AI ML वाली लर्निंग। कहाँ तक हम लोगों ने किया था, हमारा ये हो गया था और यहाँ से स्टार्ट करना था डिफिनीशन 6.1 से। और चलो पानी वानी पी के आगे बढ़ते हैं जल्दी से फड़क से। डिफिनीशन 6.1 प्रोबेबिलिटी डेंसिटी फंक्शन। फंक्शन f r to the power d to r is called a probability density function pdf। इसको करने के बाद एक क्लास लेंगे उसकी रिएक्ट जेएस की, मतलब मैं लूँगा, वो तो मैं बताऊँगा वहाँ पे पढ़। और यहाँ पे कुछ अभी चलो बढ़ते हैं आगे। फंक्शन साउंड वगैरह आ रही कि नहीं पहले चेक कर लूँ। इसमें क्यों नहीं आ रही? हेलो हेलो, माइक किसमें का ले रहा है ये? प्रॉपर्टीज, ना ना ना, मीडिया सोर्स, प्रॉपर्टीज बंद करो, माइक ऑक्स, प्रॉपर्टीज, हेडफोन, हेडसेट, ठीक। ओके दोस्तों, बढ़ते हैं आगे। फंक्शन f r to the power d r is called pdf if first for every x is element of r to the power d f x is greater than or equal to z। दूसरा है its integral exists as its integral exists and summation of r to the power d fx dx बराबर 1। और ये है वो है प्रोबेबिलिटी डेंसिटी फंक्शन। और यहाँ पे बारह फॉर प्रोबेबिलिटी मास फंक्शन of discrete random variables, the integral 6.1 is replaced by the sum 6.12। Observe that the ability density function is any function f that is non-negative and integers to 1. We associate a random variable x with this function f by p bracket a is greater than equal to x or smaller than or equal to b, which is equals to a to the b f x dx, where a and comma b is element of r and x is element of r are outcomes। अच्छा, ए बी भी एलिमेंट है आर के और ये भी एलिमेंट है आर का। outcomes of the continuous random variable x states x is element of r to the power d and are defined analogously by considering a vector of x element of r. This association 6.1 is called the law or distribution of random variable x। Remark: in construct contrast to discrete random variable, the property of a continuous random variable x taking a particular value of p x is equals to x is 0. This is like trying to specify an interval in 6.16 where a is equals to b. Set of measure 0. Definition 6.2 cumulative distribution function और cumulative distribution 6.2 है 6.2 CDF cumulative distribution function of a combination of CDF of multivariate real valued random variable capital X with states x is element of r to the power d is given by fx x p x1 is less than or equal to x1 dot 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 xt less than or equal to xt, where x1 is output x1. Right hand side represents the probability that random. यहाँ पे x जो है वो है x1 dash x2 dash t to the power t और small x है x1 x2 dash xt to the power t, and the right hand side represents the probability that random variable xi takes the value smaller than or equal to xi. The CDF can be expressed also as the integral of the probability density function, yani f of x, so that fx of x is equals to minus infinity to x1 dot 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 minus infinity to xt f z1 dot 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 z2 zd d z1 dot 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 d zt. We rewrite that there are in fact two distinct concepts when talking about distribution. First is the idea of PDF, probability density function, denoted by f of x, which is non-negative function that sums to 1 second, is a law of random variable x, that is association of a random variable x with the PDF f of x. अच्छा, एक चीज़ और थी ना उस दिन जो मैं ये वाली लिंक फॉलो कर रहा था, probability distribution where measurable transformation projection, great expectations. टावर ऑफ हेनॉय कहाँ से आ गया यहाँ? टावर ऑफ हेनॉय यूजफुल एक्सपेक्टेशन, अच्छा ये है कंप्यूटेशन प्रोबेबिलिटी. चलो we reiterate that there are in fact two distinct concepts when talking about distribution. First is the idea of PDF, which is non-negative function that sums to 1. Second is the law of random variable x, that is the association of random variable x with the PDF. अब ये है discrete distribution और ये continuous distribution. और discrete distribution में हमारे पास -1.0 से पहले की वैल्यू और 2 के बीच 10.7. ये p of x है, ये p है z is equals to z, और See example 6.3. So 0.5, 0.2. For most of this book, we will not use the notations fx and fx of x, as we mostly do not need to distinguish between the PDF and CDF. However, और ये है cumulative, ठीक है, cumulative distribution function, PDF probability distribution function. We will need to be careful about PDF and CDF sections for contrasting discrete and continuous distributions. Recall from section 6.1.2, the probabilities are positive when the 6.1.2 6.22 6.1.2 एक बार वापस से देख लो 6.1.2. अच्छा, इसका रैंडम वेरिएबल्स की बात कर रहा है. Positive and total probability sums up to 1. For discrete random variables 6.1.2, this implies that the probability of each state must lie in the interval 0, 1. However, for continuous random variables, the normalization C6.15 does not imply that value of density is less than or equal to 1 for all values. We will illustrate this in figure 6.3 using the uniform distribution for both discrete and continuous random variable. We consider two examples of uniform distribution where each state is equally likely to occur. This example illustrates some difference between discrete and continuous probability distribution. Let Z be a discrete uniform random variable with 3 states, -1.1, 0.3 और 1.5. स्टेट हो गई 3. ये है स्टेट हमारे पास और इक्वल प्रोबेबिलिटी है तीनों के आने की. ठीक है. द प्रोबेबिलिटी मास फंक्शन कैन बी रिप्रेजेंटेड. अरे यार, 1 मिनट दोस्तों, थोड़ा सा वेट कर. ठीक है, तो alternatively we can think of this graph ऊपर बना है वो, where we use the fact that 6.3 है ना ये वाला. हाँ, ये ग्राफ इस डेलिब्रेट. अरे यार, तो क्या कर रहा है? is deliberately extended so that it is it the same as figure 6.3b. Let x be a continuous random variable. Random variable taking values in the range 0.9 or 1.6 से छोटा, as represented by figure 6.3b. Observe that the height of density can be greater than 1. However, it needs to hold that 0.9 to 1.6 px dx बराबर 1 can be discrete. यहाँ पे point probability है mass function not applicable. Interval probability यहाँ पे not applicable. Continuous में PDF है और ये है commutative function interval. There is an additional stability with regards to discrete probability distribution. The states Z1 to Zd do not in principle have any structure, that is there is usually no way to compare them. For example, Z1 रेड दे दिया, इसको ग्रीन दे दिया, इसको ब्लू दे दिया, तीन स्टेट अलग अलग. However, in many machine learning applications, discrete state take numerical values, जो कि था ऊपर दिया था -1, 0.3 और 1.5. Here we could say Z1 less than Z2 less than Z3. Discrete states that assumes numerical values are particularly useful because we often consider expected values of random variables. Unfortunately, machine learning literature uses notations and nomenclature that hides the distinction between the sample space omega, the target space t, and the random variable x. For a value x of the set of possible outcomes of the random variable x, x is element of t, x denotes the probability that random variable x has the outcomes x. For discrete random variable, this is written as pxx, which is known as the probability mass function. The PM is often is called probability density function, referred as to many things. Even further, the cumulative distribution function is often also referred as the distribution. In this chapter, we will use the notation x to refer both univariate and multivariate random variables and denote the state by x and respectively. We summarize the nomenclature. It's remarkable using expression probability distribution not only for discrete probability mass function but also for continuous probability density function. Although this is technically incorrect, in line with most machine learning literature, we also rely on context to distinguish the different uses of the phrase probability distribution. Sum rule, product rule, Bayes theorem. अब sum rule और product rule तो the first rule, the sum rule, states that px summation of p x comma y if y is discrete, if y is continuous, y continuous होगा तो हमारा ये चलेगा, और y discrete होगा तो summation of y is element of y px comma y, और y यहाँ पे है, y are the state target space of random variable. This means that we sum out or integrate out the set of state y of the random variable y, where y are the states of target space of random variable y. This means that we sum out or integrate out the set of states y of the random variables y. The sum rule is also known as marginalization property. The sum rule relates the joint distribution to a marginal distribution in general when the joint distribution contains more than two random variables. अच्छा, more correctly, x is equals to x1, x2, x3 dot d. We obtain the marginal. अब फिर उसके बाद यहाँ पे है प्रोडक्ट रूल, जो कि होगा पी एक्स कामा वाई इक्वल्स टू पी और वाई और एक्स to px. Very important variable can be sum rule हो गया ये, और ये है product rule, लिख लो इसको. Sum rule p of x is equals to summation of y element of y px comma y if y is discrete, summation of y integration of y यहाँ पे p x comma y dy कब होगा ये? इफ y इज कंटिन्यूस, y कंटिन्यूस होगा तब। और प्रोडक्ट रूल में क्या है? प्रोडक्ट रूल हो जाएगा पी एक्स कामा वाई इज इक्वल्स टू पी वाई एक्स पी एक्स। The machine learning and Bayesian statistics, we are often interested in making interference of unobserved latent random variable. Given that we have observed that random variable, let us assume we have some prior knowledge of px about an unobserved random variable x and some relationship py of or x between x and second random variable y, which we can observe. If we observe y, we can use Bayes' theorem to draw some conclusion about x. Given the observed value of y, Bayes' theorem, या Bayes' rule और Bayes' laws, Bayes' theorem चाहे बोल लो, चाहे इसको हम लोग बोल सकते हैं Bayes' rule और बोल सकते हैं Bayes' law। p x, y जो कि है posterior is equals to p of yx और p of x upon p of y। ये हमारा likelihood ये है prior और ये है evidence। is direct consequence of the product rule since and p x comma y yx p x so that p of x or y, p of y is equals to p of y of x or p of x is equals to p x or y to p y x p x upon p y is the prior which encapsulate our subjective prior knowledge of the unobserved latent variable x before observing any data. We can choose any prior that makes sense to us, but it is critical to ensure that the prior has non-zero PDF or PMF on all possible x, even if they are very rare. The likelihood p of I, y or x describe how, in the case of discrete probability distribution, it is the probability of the data y if were known the latent variable x. Note that the likelihood is not the distribution in x but only y. In y we call p y of x either a likelihood of this or given probability y of given x, but never the likelihood of y mac k. The posterior is the quantity of the interest Bayesian statistics because it's express exactly what we are interested in, what we know about of x after having observed y। तो ये बनेगा द क्वांटिटी आ जाएगी e ऑफ, इसको क्या हो गया, ठीक है, y p of y x p x dx e x p y or x is the marginal likelihood evidence. Is the marginal likelihood evidence. The right hand side of this uses the expectation operator, which we define. The marginal likelihood integrate the numerator and numerator of this respect to the latent variable x. Therefore, the marginal likelihood is independent of x and it ensures that posterior normalized. The marginal likelihood can also be interpreted as the expected likelihood, where we take the expectation with respect to the prior. Beyond normalization of the posterior, the marginal likelihood also plays an important role in the Bayesian model section. As we will discuss this, due to the integration, the evidence often hard to compute. Bayes' theorem allows us to invert the relationship between x and y. अच्छा, given by likelihood. Therefore, Bayes' theorem is sometimes called the probabilistic inverse. We will discuss Bayes' theorem further in section 8.4. First, it is the quantity interest in calculate the orbital information prior to the data instead of the carrying the posterior around it is possible focus on such as example maximum posterior, which we will discuss in section 8.3. And focusing on some statistics of the posterior leads to loss of information. Focus on some. If we think in a bigger context, then the posterior can be used within the decision-making system, and having the full posterior can be extremely useful and lead to decisions that are robust to disturbances. For example, in the context of the model-based reinforcement learning, D. North et al. So that using the full posterior distribution of plausible transition function leads to very fast data maximum possibilities, and having full posterior can be very useful for downstream tasks. We will continue this in the different innovation. ठीक है भाई, इसको कल पढ़ेंगे। अभी की क्लास ओवर करते हैं।